In this video, we're going to talk about electrophilic substitution. We're going to talk about what is an electrophile, then we're going to go on to chlorination, bromination, alkylation and acylation. We're then going to talk about the reactivity of benzene versus phenol and cyclohexene. So what is an electrophile? It is a substance that accepts a pair of electrons to form a dative covalent bond. Now it's got here positive or delta positive charge. That's not part of the definition, but it helps you recognise whether it's an electrophile or not. Okay, it accepts a pair of electrons, and the electrons are negative, so therefore they're attracted to this positive or delta positive charge to form this dative covalent bond. And we'll go through the mechanism of how it works during the video. Now examples of electrophiles are the nitro, NO2+, which is used in nitration. Again, you see this plus. Then CH3, which is used in alkylation. And then an acyl group, again with that plus, which is used in acylation. Now these are all ones with full plus charges. Okay, so they'll accept a pair of electrons to form a dative covalent bond. But also what happens is you can have molecules with permanent dipoles. So you can see here the hydrogen is a delta plus and the bromine is a delta minus. The bromine is more electronegative than the hydrogen. There's a difference in electronegativity which causes this to have this permanent dipole. Now that means the electrophile, which accepts the pair of electrons, is this H here, okay, with the delta plus. You can also have an electrophile with Br to Br or Cl to Cl, but that dipole is not naturally occurring. That's caused by them getting close to a double bond, okay? So you can have that as an electrophile, but it doesn't naturally occur because they have the same electronegativity. But you will see in electrophilic addition, for example, that this dipole exists because of the repulsion of the electrons by the double bond. So it is in fact an electrophile, even though it wouldn't normally have a dipole. Now, mechanisms for electrophilic substitution of benzene, okay, are all of a certain type. So if you go to and do the general mechanism once or twice, you can apply it to everything else. So it's really good learning how to do it. So first of all, we take benzene, and we take our electrophile, which we call A+. We take a curly arrow, and we start it from this delocalized ring of electrons, okay, to the atom. So not to the plus, to the atom. As you can see, there's our arrow going from the delocalized ring to the electrophile. We then look at our intermediate. Our intermediate has lost 2 electrons. Those 2 electrons are gone from inside the ring. Okay, because this arrow is the movement of a pair of electrons. So it's a pair of electrons. So if that pair's gone out, there are 6 electrons that are going around here. That means I've taken 2 out of the 6. If you think of the 6 sides to a hexagon, okay, that means that I remove 2 sides of this circle. Can you see I've taken the part of the circle that's that side and the part of the circle that's that side. So I've taken out 2 sections of the circle, which means I've removed 2 electrons. Those 2 electrons have gone to the bond to the A right here. And we call that a smile of the clown's face, essentially. So it looks a bit like a clown's face if you look at it with a plus. Okay, and it must go from 2 to 6. So this would be 2 and this would be 6. And it should be where the electrophile is joined on. So if the electrophile is joined here, then the circle here goes around where the electrophile is bonded. So at that point, you then need to take the pair of electrons, and the curly arrow comes from the bond to the positive charge. So there's the pair of electrons in the bond between the hydrogen and the carbon. And that's going to go back in. That will restore the 2 electrons. So it'll restore the 2 electrons that I took out. Remember, I took 2 electrons out here. I'm putting another 2 electrons back in. It's not the same 2 electrons. It's the 2 electrons between the carbon and the hydrogen. And that then restores our delocalized ring. It now has 6 electrons in it again. So we've gone from 6 electrons, we've gone to 4 electrons here, and then back up to 6 again. And that means the hydrogen has lost its electron, And so the hydrogen is a H+. It's lost its electron because both electrons are in the ring. And this is your general mechanism which you should learn, okay, for electrophilic substitution. But we'll go through many examples in the video. So the first example is electrophilic substitution nitration. So here we have our benzene, we're adding it to concentrated nitric acid and concentrated sulfuric acid, and it's at less than 50 degrees. And you'll get one nitro group if it's less than 50 degrees, just the one, and you make water. Now, being able to do that equation is one of the skills, but there are lots of skills to do with nitration that you'll need to learn. One of them is generating the electrophile. So we have to generate the electron. This is often a question in an exam. What is the equation for generating the electrophile? Okay, and you have the sulfuric acid plus the nitric acid. Okay, and then that makes your electrophile, which is in the green here, which is NO2 plus. Okay, and then you've got HSO4 minus and H2O. And I'm afraid you do need to memorize that. It's quite a lot of memorizing, and we've gone over how you can do that. Flashcards, for example, can help you do that. So we've made our electrophile. Okay. After that, we're going to do the mechanism. Now, it uses the general mechanism we had in the last slide. So if you want to have a go at just doing it with the electrophile, feel free to do so. Stop the video and have a go. So here's the mechanism. We've got our electrophile, we've got the ring. We take two electrons out to form a dative covalent bond with the electrophile. We've done our clown's face, okay, and we've done the missing two parts here where the two electrons have gone out. We're now going to put our electrons on the hydrogen, carbon-hydrogen bond, and put those electrons back in to restore the ring. And that then gives you your nitrobenzene. Now we're missing our H+. So our H+ is gone because it's lost that electron, but it's the same mechanism as you had before. We also need to know our catalyst mechanism. And our catalyst mechanism is about something that's used up, which we have the H2SO4 here, and then regenerated. So let's have a look at how we regenerate it. We take the H+, which I've just highlighted over here, and we're going to react that with our HSO4-. So our HSO4- from here is going to react with our H+. That brings back your H2SO4, which means it is regenerated. So it's a catalyst. So if something's regenerated, used up and regenerated in a reaction, it's a catalyst. Let's talk about other aspects of nitration. So the full equation can be done like this. C6H6 plus HNO3 goes to C6H5NO2 plus H2O. And you can put your reagents and your conditions on there. Okay, you must state that both the acids are concentrated. Okay, and you can write it as conc as well as that temperature of less than 50. Okay, now you can also write it in skeletal formula like we did in the previous slide. Okay, and you can have your water as a product. Now if you go on the previous slide, you can figure out the products and the reactions because everything cancels out to create the full reaction. But remember, really important, you use one nitric acid and you produce one water every single time the benzene is reacted with concentrated nitric acid and concentrated sulfuric acid at less than 50. Now let's look at multiple nitrations. Now you can get multiple nitrations at any temperature greater than 50 degrees. Okay, so that means you could get trinitrobenzene. Now that does that at about 150 degrees, but you're not expected to remember the temperature just. If it goes greater than 50, you can either put 2 on or 3 on. Now, if I'm going to put them on, it's really important you remember this exam tip. If given a higher temperature than 50, always remember 1 nitric and 1 water is produced per nitration, just like we showed you in the last slide. So let's look at an example here where we've got our conditions, but it's greater than 50. So we're just going to say greater than 50, we're going to put 3 on. So we've put 3 of our nitro groups on. That means we put our reactants, nitric acid and water, but it's 3. So it's 1 nitric acid per nitration, 1 water per nitration. So we have to put 3 and 3 there to say that we've used 3 of the nitric and made 3 of the water. We don't change our sulfuric acid because it is a catalyst. We're now going to look at chlorination. To do chlorination, you must add chlorine and use a catalyst, AlCl3, to create chlorobenzene plus hydrochloric acid. Now, to do that, you need to generate the electrophile. And the electrophile is done using AlCl3, which is also known as a halogen carrier. So it carries the halogen. So you'll see it referred to often as a halogen carrier. And benzene will not react without a halogen carrier. So it won't react, in this case, with chlorine unless it's got a halogen carrier. So that happens in chlorination, bromination, alkylation and acylation. All of them, they need a halogen carrier for them to work. And you'll see that being repetitively done over the next 4 reactions. So let's look about how to generate that electrophile using the halogen carrier. So the electrophile is produced with the aluminium chloride bonding with the chlorine and creating AlCl4- plus Cl+, which is our electrophile, the Cl+. Now you can do that with iron chloride instead, it's the same reaction, or you can do it just with iron. Again, same reaction, but the balancing is slightly different. All 3 of them will work. Now, if you're going to turn this from chlorination into bromination, you have to replace all of the chlorines with bromine. That means you have to replace all of them in the electrophile equations. Okay, so you have to do it here, here, and here, depending on which one you're using. So make sure you do. And also you'll have to replace them here, 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 and here, if you're doing the full equation. But let's concentrate on chlorination for now. So chlorination is about generating the electrophile, which we've already gone over. So AlCl3 plus Cl2. And there's our electrophile that is produced. Now, we'll come back to AlCl4- in a second. We now want to take our electrophile and do the mechanism. And the mechanism, taking the electrons out from there to the Cl+, like in the general mechanism that we did. And then we go to the clown's face, as I called it, okay, which you draw here. And then we go to the electrons. We take those electrons back in, break the bond between the C and the H, okay, and restore the delocalized ring. We then turn it into our product plus our H+, because our H+ here has left. We then regenerate our catalyst by taking here, the AlCl3 has turned into the AlCl4-. That AlCl4- is going to react with the H+ that's produced over here. Okay, and we've got it here. AlCl4- plus H+ goes to the AlCl3 plus HCl. And it's really important you know all of these equations. Now you notice your AlCl3 is regenerated, so a catalyst. Now let's do this with bromination. What I recommend you do is I'd stop the video and I'd just do it with bromination yourself and see whether you can do it, and then I'll go through the answers. So here we have the electrophile equations again. Okay, and we're choosing AlBr3 this time, but you can do FeBr3 and Fe. Then we're going to make that HBr, okay, because remember, we're doing Br, not Cl, and we put on the Br, and we're using aluminium bromide and bromine. So let's look at all the equations. Generating the electrophile is AlBr3 plus Br2, and here's our electrophile, this time Br+. We then do our mechanism, taking the electrons out of the delocalized system, 2 of them, to the Br+. We then create our smiley face, missing 2 electrons, so we put the 2 electrons back in. That restores our delocalized ring, okay, and gives us our H+. The H+ is then going to react with our AlBr4-, okay, and then we will get our AlBr3 and HBr. And this is our final product here, and here's our catalyst. So we know we've got AlBr3 at the start, and we've got AlBr3 at the end, so it's regenerated, so a catalyst. Now you'll see this repeated again in the next one, which is alkylation. So Friedel-Crafts alkylation, again another electrophilic substitution, all of these are. You take a halogenated alkane, doesn't have to be CH3, it could be something longer. Okay, so it could be chloroethane, chloropropane, chlorobutane, chloropentane. The length is up to you, the branching is up to you. Okay. You then take our halogen carrier, AlCl3, and again you'll create this HCl, okay, because you're dealing with chlorines, okay, and you'll put this time your CH3 on the benzene. So let's talk about our different types of equations that we've got for Friedel-Crafts alkylation. Generating the electrophile. So that's going to be our halogen carrier, our catalyst, reacting with our chloromethane. Chlorine's going to react with the AlCl3 like it did in every other example, and you leave the CH3 plus as your electrophile. Now this is one of the unfamiliar mechanisms that you have to get used to. We say unfamiliar because even though some of these mechanisms are not strictly required, you will actually have to recognise them and recognise how they're used because they can be put in an exam. It really is based upon your understanding of the movement of electrons, not in you memorising the mechanism. But the mechanism in this case is the same as all the other mechanisms that we've used for electrophilic substitution. So here we have our electrophile. Let's take the electrons out again. We then go make our smiley face. Then take our electrons again, put it back in. Then we create our substituted benzene, this time with a methyl, and our H plus again. We then regenerate. Okay, we take the AlCl3, let's create our AlCl4, and then plus the H plus, and then we regenerate our catalyst again, and then we have our final product again. So you can see that this is exactly the same as chlorination, bromination, and nitration. It should be becoming familiar, hopefully, by now. The next one is Friedel-Crafts acylation. Okay, and you have an acyl group. So here is an acyl group, CH3CO. That's an acyl group, and we have to use a acyl chloride, which this one is called ethanoyl chloride, and we use our halogen carrier again. And this will put an acyl group onto your benzene, plus the HCl as we've had before. So we're going to do the same thing, generate the electrophile. We take the AlCl3, add it, and we've done it in skeletal formula here, but you can do it if you're not sure about things, draw it in displayed. Okay, and you can see that this acyl group, which is the CH3CO, is going to bond with this AlCl3. All that's going to happen is the chlorine is going to bond with the AlCl3 again. That leaves the acyl group behind with that positive charge and this AlCl4 again. Very similar as you've done. But that's your electrophile. So if we put this in here, again, all we need to do is take the electrons from there to the atom with the positive charge. We then draw a smiley face. Okay, take the electrons back in again. This then creates our product and our H+. And then we can also do our catalyst again. And our AlCl4, which is produced up here, is reacted with the H+ that's produced in the mechanism and creates our catalyst again. So I'm hoping that you can see that throughout all of these there are similarities. The mechanism is exactly the same, whether it's acylation, alkylation, nitration, okay, or chlorination, or bromination. Now I'm going to go over how to structure your answers related to the reactivity of benzene, phenol, and cyclohexene with bromine. These rules would apply to reactions with chlorine as well. So when we're answering questions that are related to the reactivity of benzene, phenol, and cyclohexene with bromine, and they are very common, so this is a very common exam question, worth anything from 2 to 4, maybe 5 marks. Okay. First of all, explain the reasons, nature and extent of delocalization or localization. So for example, are the electrons localized or delocalized? And we'll talk about the examples next. Then relate this to electron density, just low or high in each case, and discuss the extent of polarization of bromine or attraction to the electrophile if you've got an electrophile that's NO2+, for example, or Br+. Polarization is just for when you have created a dipole, but we'll talk about that in a second. And then explain what's needed to make them react. For example, you need to have a halogen carrier for benzene to react. It probably doesn't make too much sense now, but it will do when I go over the next example. So, typically they ask you one of 3 things. So it's either cyclohexene bonded being compared to phenol, or cyclohexene being compared to benzene, or all 3 being compared. So let's look at the reactivity of all of these. And what essentially we're doing is looking at the reactivity of alkenes versus benzene versus phenol. It doesn't have to be cyclohexene, although it often is. It can be any alkene at all. It's the same answer. So which one is more reactive when it comes to, for example, reaction with bromine? So cyclohexene, okay, it's got that double bond. Now, if you remember the mechanism of this, which is electrophilic addition from right at the organic start in usually the AS year. Okay, I put a dipole on here because the bromine is coming towards the double bond. Double bond is negative and therefore it repels the electrons in this bond away, making this dipole. This dipole then creates the electrophile and the electrons from the double bond come out to form a bond with one of the bromines. Now, that pair of electrons in the middle then go out to the bromine to form Br-. Okay, and then the Br- comes in, and you notice, hopefully again, arrows come from where electrons are. So this is coming from a lone pair of electrons to the positive. And that is the mechanism, which hopefully you've done before, of electrophilic addition of a halogen to an alkene. Now, we form a dibromo cyclohexane molecule, so 1,2-dibromo cyclohexane. Okay, and this is a test for unsaturation. So this is a test for unsaturated molecules. So this means it will decolorize, and you can know whether it's an alkene or not. Now, benzene can have bromine added to it, but we've just done this, and benzene with bromine added to it needs a halogen carrier. So there's no reaction without a halogen carrier. Whereas cyclohexene reacts without a halogen carrier, no problem whatsoever. You get polarization here, okay, and that's because of localized electrons here, polarization here, and high electron density here, but we'll talk about that in a second. We've got delocalized electrons here, low electron density because they're separated, and you can't do it without a halogen carrier. Now, phenol. Phenol does react with bromine, and it reacts with bromine really well. Now, it reacts 3 times, so three bromines, and creates HBr every single time it does the reaction. So those bromines are going to go at 2, 4, and 6. So that really important, if you're reacting phenol with bromine, it goes in the 3 positions unless there is something already on those positions. So if you've got a phenol and there's something already on those positions, don't put another bromine on. 2, 4, and 6 is where it reacts. Now, because I'm doing it 3 times, I have to use 3 bromines, and I produce 3 HBrs. Now let's talk about this in terms of the actual reactivity and in terms of how do you answer the question. So we said on those questions there's 3 different parts. One was it delocalized or localized? Well, there's the 2 orbitals, the pi bonds above and below the plane of the sigma bond, okay, and the electrons are localized there. And because they're localized and stuck in one spot, it's of a high electron density. That polarizes, forces those electrons away, giving you a dipole, and your mechanism is there. So if we start thinking about that, the question said, is it delocalized or localized? Okay, has it high or low electron density? Is it polarizing or not? So in your answers to this question, just answer those three questions. So first of all, it is localized, it does have a high electron density, and it does polarize the bromine. That's 1 or 2 marks straight away in a very large 5-6 mark question. We then go to benzene, and let's look at those electrons on benzene again. Okay, and they're going around in a circle above and below the plane, okay, in this pi bond. But they're delocalized and they're far apart from each other. You can see them appear. Now you can see how far apart they are compared to those electrons. So it's a low electron density. And that means it doesn't unless you have a halogen carrier, so it doesn't polarize. So it's delocalized, it's a low electron density, and it's not polarizing, needs a halogen carrier. We then talk about phenol. Phenol, really important here that when you're answering the question, you talk about these lone pairs of electrons that are on the oxygen. The lone pairs of electrons go into the delocalized system. You can see here the delocalized system, they're part of it, and it's a bit like a bowling pin shape, but they're part of it. That means you have many more electrons, and because there's many more electrons, because of the lone pairs of electrons delocalized into the ring, you have a high electron density, and therefore it is polarizing. So we've got, if we just mention, notice how little words we've used, but yet we've hit every single mark when we're comparing the reactivity of alkenes to benzene and phenol. Remember, you won't necessarily get all 3, you might get 2 of them, but just stick to these 3 points. Is it delocalized, localized, has it got a high or low electron density, and is it polarizing, and give reasons why. So if you look at phenol with bromine, we talked earlier about the fact that the phenol will react at 2, 4 or 6 position, and you need 1 bromine per substitution. And you create 1 HBr per substitution. But I just wanted to show you, even though they're going 2, 4 or 6, only place them on, as I said before, only place them on if they have a hydrogen on and no functional group on them. So let's look at an example. So here we have an OH here, but an NH2 here. Well, normally, if I was reacting it with bromine, I would put the bromine here, but there's already something there. So I'm not going to put the bromine on that carbon, because it's at position number 2. That's where I'd normally put the bromine if I was reacting it. 2, 4 or 6. Now, that means, because of that functional group, I only put 2 bromines on, and I put them in the 4 and 6 positions. That means I've done 2, which means I need to balance it out properly, okay, and I need 2 bromines and 2 HBr as a result. So I've talked about the question about what is the difference in reactivity between alkenes, benzene and phenol, and I've put that in a table with some simple lines that you have to follow. Okay, but I thought it would be useful to actually put it in the structure of a question. So here is a question. Explain the relative resistance of benzene to reaction with bromine compared to the reaction of bromine with phenol and cyclohexene. Now, you can try that now, but the actual answer is cyclohexene reacts with bromine because it has localized electrons. So that's our first point. Remember, we talked about delocalized or localized. Okay, and has a high electron density. So we've done our marking point number 2, which allows it to polarize. So our marking point number 3. Now, we then talk about benzene. Benzene does not react with bromine without a halogen carrier. So again, another marking point. This is because it has delocalized electrons. So again, we're going on this localized, delocalized. And therefore, we're talking about electron density again. Phenol reacts with bromine due to lone pairs of electrons. Again, we're talking about where do those electrons come from, donating into the delocalized ring. So we're saying it's delocalized. Okay, and that gives a high electron density, again, electron density, which polarizes bromine again. So here is how you would put it in the form of a question and the question's answer. And all we're doing, though, is picking those 3 points and going over those 3 points again. Lastly, we're going to go through some unfamiliar mechanisms, and these are all of electrophilic substitution. So I'm going to show you the general way in which they'll be done. So they'll be done by basically giving you benzene and then adding an electrophile. So the electrophile in this case will be carbon dioxide. Okay, so you've got carbon dioxide, and in there you then create this product. Okay. So you've created this product. So I want to know what is the intermediate of that product, and I want to know what are all the mechanisms. First thing I have to do is I have to look at this and I have to say, where are my dipoles? So I can see oxygen is more electronegative than carbon, so my dipole is there. I then feel I've got my electrophile. My electrophile is usually delta plus or plus. Okay, and then I look at my benzene and say, well, how does that fit electrophilic substitution? Well, electrophilic substitution usually has the arrow going from the delocalized electrons to the carbon. So there I have my arrow. The clever bit then is then to look at the different reactants and product and say, what's different between the reactant and the product? Well, so here I have a product which has a single bond oxygen and a double bond oxygen here. So that double bond has to break. Another way of working out is that carbon has 4 bonds. It's got 4 bonds already, and then this pair of electrons that's moving from the delocalized area is another bond. So that's 5 bonds. Can't have 5 bonds, needs to have 4. So what I do is I want to break one of those bonds so it creates this. And I want to make sure the minus is on the O. So I take a pair of electrons and I put it on to the O. That means I'm taking 1 electron from the oxygen itself and 1 from the carbon. That extra carbon electron, which wasn't with the oxygen, is this negative charge here, which means that you take the pair of electrons and put it there. Now I have to figure out the intermediate between there and there. So all we do is follow the arrows through. So if that is the case, here's my benzene again. I'm going to put the bond here. So therefore my smiley face points towards where I'm putting the bond. This is my smiley face. And then I can go, here's my carbon. And there is my O minus. Now what we're missing here, think about electrophilic substitution. We're missing that H that is there. This H is going to become that H down there. Therefore it needs to lose its electrons because it is a plus. It loses its electrons by doing exactly what we do in all the other mechanisms, okay, which is taking the electrons from the bond into the plus to get rid of this plus charge, put the 2 electrons back in, and then this hydrogen loses its electron. Remember, 1 electron in that bond is from the hydrogen, 1 is from the carbon. We're taking both electrons and put it back in, which means the hydrogen loses an electron and becomes H+. And that is an unfamiliar mechanism, not on the course, okay, but can easily be asked. And we're going to go through another unfamiliar mechanism now. Now, if you look at our last example, try and do this example here. See if you can do the intermediate. You'll see it's very similar to before. Now, let me take you through it. If you look here, we've got sulfur and an oxygen. Different electronegativity, because the different electronegativities, there will be a dipole. Now I understand there will be no overall dipole because it cancels, but there still will be a dipole on each element, it just cancels overall. So if we go here, there's our negatives, positive, and there's our negative. Okay, so we've done our dipole, so we've got our first mark in our exam. We then take our electrons again from there to the atom. And again, we've got too many bonds. And again, look down here. See, we've already drawn it for you this time. There you go. There's an electron here causing this negative charge, there's a lone pair of electrons which has come from that bond onto there. Okay, so there you go. Looking very much like before. All we do is draw it again. Okay, and as we do that, let's look where the sulfur is bonded. It's here. So therefore there's my smiley face, okay, because it's going to bond here. And then you put your sulfur as is there. Okay, and then your H is coming out like that. So your H is coming out. Too many bonds here. We want to cancel this positive, so we take those electrons back in. Okay, that will mean that this will go to this, and you'll have your H+. And this is an unfamiliar mechanism because it's something that you are not familiar and haven't come across, but at the same time it's familiar in terms of its electrophilic substitution.